Hey everyone, today I'll be talking about constructing Pseudorandom generators for positive spectrahedra. This is joint work with Penghui, who's at Nanjing University. So the starting point of this work is constructing linear programs. So what is a linear program? It is just an optimization problem where we optimize a linear function over a polytope. Right, so now let's just say how does the linear program look like mathematically? So it is defined by k vectors in Rn, W1 to Wk, and constraint matrix C. And it kind of is just like optimizing a linear constraint that is C transpose X. So C is an n-dimensional vector, X is an n-dimensional vector, so C transpose X is a number. So you want to maximize C transpose X subject to k constraints. And these k constraints are Wi inner product with X is at most theta I. So Wi is again an n-dimensional vector, X is an n-dimensional vector, the inner product is a real number. So you have k different constraints, X should satisfy all these k different constraints. So that is your feasible region, and you're maximizing a linear function subject to these k constraints. So that's a linear program, and opt is the optimum value of this linear program. And what's nice about linear programs is efficiently solvable. Efficient means that it's polynomial in k and n. And if you'd like to approximate opt, it's also polynomial in 1 over epsilon, if you want an epsilon approximation. So let me break down this linear program into slightly more simpler objects to understand the feasible region of a linear program. First is the concept of a half space. So what is a half space? So half space is just a constraint that breaks down Rn into two pieces, a 0 region and a 1 region. So a half space that is defined by this vector W, think of W as a vector in Rn, similar to the above here. So W is a vector in Rn, and X is an n-dimensional vector, X is an n-bit Boolean string. So we say the half space H defined by W is 1 if and only if the inner product between W and X is at most theta. In other words, we can write this half space as just as this indicator function, where the inner product between W and X is at most theta. So that is a single half space. Now let's look at what's a polytope. So polytope is just a collection of half spaces. In particular, it's just an intersection of half spaces. So think of Wi as an ith half space, and theta I is just defines the ith half space. Then a k-facet polytope is just the feasible region of the intersection of H1, H2, all the way to Hk, where again Hi is just the indicator function if the inner product between Wi and X is at most theta I. So that is a polytope. In other words, you can view the linear program as just maximizing a linear function that is C transpose X subject to X line in the polytope. So linear program is just maximizing a linear function over a polytope. That's precisely the first point in the slide. And linear programs have found several applications, for example, in optimization, in combinatorics, in geometry, and in computational complexity. Next, I'm going to be looking at a generalization of linear programs that's going to be the theme of this work. Those are semi-definite programs. So what is a semi-definite program? So semi-definite program still optimizes a linear function. So it's going to still optimize C transpose X in the previous slide, but the feasible region is going to be a slightly richer object, and this richer object is called a spectrahedron. Now, a general semi-definite program still has very similar structure to what a linear program was, but over a richer object. That is, the richer object is going to be defined by matrices now, no longer vectors. So W1 to Wk are symmetric n by n matrices, and B is also a symmetric n by n matrix. And the opt, or the optimum value of the semi-definite program, is still a linear function that is C transpose X, subject to a linear matrix inequality now. So X1, W1, all the way to X and Wn, you sum all these matrices up. Recall X is a bit string. So X is just Xi is just a real number. Capital Wi is a matrix. Summation of Xi Wi is at most B. And what I mean by at most, that means that this is the loner ordering. That is, the right-hand side minus the left-hand side is positive semi-definite. That means all the eigenvalues are non-negative. So first things first, the spectrahedra, or the geometric object spectrahedra, is very complicated in the sense like it could be a lot more complicated than just a polytope. For example, a spectrahedron could be a cylinder. It could be this weird looking object. So it's a lot more complicated than just a polytope. But at least one nice thing is it at least generalizes linear programs. So if you think of W1 to Wk just to be diagonal matrices, diagonal n by n vectors, for example, then this condition in lower ordering is just nothing but a polytope. And although it generalizes linear programs to matrices, it is still solvable in polynomial time, polynomial in n and k, and even in approximation factors. If you'd like to approximate, opt. But unfortunately, spectrahedra are not as well understood as polytopes. For example, even basic things like, for example, like the noise sensitivity, the surface area, and things like that are still we are learning about them right now. It's not as well understood as polytopes. So these are the geometric objects that I'll be talking about in this talk. And the next thing, again, the most important thing is semi-definite programs have actually found a lot of application. For example, in approximation theory, sums of square hierarchy, in quantum computing. So SDPs have also found their way in a lot of these applications. So again, these are the two things I'll be talking about in the first part. And the second part I'll be talking about is pseudorandom generators, which I'll define now. So what is a PRG? So pseudorandom generator is just a function. It's a function that expands randomness. In some sense, it takes like R bits, which are like pristine random bits, and expands it to N bits, which we call pseudorandom bits, which look uniform, which kind of look uniformly random, but are not exactly uniformly random, because they've taken R purely random bits to N pseudorandom bits by this function PRG. So PRG is, so we can define a PRG for a function of classes, for a class of functions. So we say script C is just a subset of all functions, Boolean functions, and we say G fools a subset of Boolean functions if it satisfies the following. So for every function in the function class, the function f cannot distinguish whether it was given uniform random input or a pseudo-random input. So again, what I mean by pseudo-random input, first I pick a uniformly random R bit string, I feed it into G, I get an N bit string out. Now I feed in F either a uniformly random U or I feed it a pseudo-random G of X. And F in this concept class cannot distinguish which one it was given as input with bias greater than epsilon. So we say G is an epsilon PRG for this class of functions. And what's important is the seed length. The seed length is the amount of pristine input bits, uniformly random inputs with bits it needs to be given to produce N bits as output. And of course, the holy grail is to have like the seed lengths to be polylogarithmic in the parameters that define the function class. For example, one interesting function class that many people have been, the entire field of like half the theoretical computer science we have looked at is like the class of polynomial size circuits. So if you could fool the class of polynomial size circuits with polylog, with seed length polylog, that would imply BBP equals to P, which would be a dramatic breakthrough. But another subset and a simpler question that people have also looked at is, can we construct pseudorandom generators for geometric objects? For example, if script C was just a polytope, was a half space, and so on. And constructing PRGs for geometric objects has been a rich area of study, which I'll overview in the next slide. So the first line of work was started by Diakonikolas et al. And Meka Zuckerman in 2009, where they showed how to construct PRGs for half spaces. And there have been a lot of subsequent works that have improved these PRGs with better seed length dependence. Simultaneously, there was another line of work that was started by Harsha, Clemens, and Meka in 2013, where they construct PRGs for polytopes. And the point, as I said, like polytopes generalize half spaces, so the techniques that were involved to fool polytopes was much more richer than those involved to fool half spaces. And this line of work was kind of mostly culminated by O'Donnell and Cerveria in 2019. And simultaneously, there's been another line of work for fooling polynomial threshold functions. So these are functions which are just given by the sign of a polynomial acting on x1 to xn. Again, PRGs for PTFs was started by Meka Zuckerman in 2009, and there's been a lot of works in this direction, but it's been a lot more tough to construct PRGs for PTFs compared to half spaces and polytopes. And in a way, putting all these three things together, spectrahedra naturally generalizes half space and polytopes, and in a way also generalizes polynomial threshold functions, because you can view the determinant of a matrix kind of as a polynomial in the dimension of the matrix. There's a slightly more deeper connection to this, but I won't get to that in this talk. So in a way, spectrahedra generalizes this line of works on fooling half spaces, polynomials, and polytopes and PTFs. And the question that I'm trying to address in this talk is, can we construct pseudorandom generators for spectrahedra? Good, and let me give you the main result of our work. So recall that what's a spectrahedron is just summation xi ai at most b, and x is just a bit string -1 to the n. And I'm going to make certain assumptions on the spectrahedron. So in this work, we are not able to fool arbitrary spectrahedra. We are only able to fool a subclass of spectrahedra. And the subclass of spectrahedra require these two main assumptions. One is positivity. So we're going to assume that AIs and the Bs are positive semi-definite. That is, all their eigenvalues are non-negative. I'm going to assume, just for simplicity, that the semi-definite program is bounded with, or the summation AI square, as the eigenvalues of this is at most capital M. The seed length will depend on capital M. And finally, I'm going to make another assumption called the regularity. So the regularity says that all these matrices have eigenvalue at most tau for every I. Right. So the main result is the following. We give a pseudorandom generator G that takes R bits to N bits, where R, which is the seed length, is logarithmic in N, and polylog in K, M, and 1 over delta. Recall K is the dimension of these matrices AI and B. And delta is a parameter with which G can fool the spectrahedra. And in other words, the point is, if you give me a uniformly random bit string or give me a pseudo-random bit string, deciding whether it lies in S, it cannot be done with bias greater than delta. So the point is, deciding whether G of X is in S or uniformly bit string is S could be done with bias at most delta. And this is the main result of our work. And the main technical contribution, which I'll be talking about for the rest of this talk, is an invariance principle for positive regular spectrahedra. So this is the main technical contribution. And the proof of this goes very similar to the work of Arunachalam in 2013. And for the next couple of slides, let me first sketch how do they prove an invariance principle for polytopes. And based on that idea, we will carry on to prove invariance principles for positive regular spectrahedra. So recall, what's a polytope? As I said, it's just a collection of K half spaces, intersection of K half spaces. So W1 to WK is a half space, and I take the intersection of them, that's a polytope. I can also write this in the matrix form. Think of W as a K by N matrix, where each row is Wi. So W1, W2, all the way to WK, that's a K by N matrix, and X is an N-dimensional vector. So Wx is a K-dimensional vector, which should be at most θ1 to θk. So a polytope can just be written as Wx at most θ. And the main invariance principle for the Harshad-Clemens-Mecca proof was for regular polytopes. And regular here means that all these vectors Wi have the L2 norm at most tau. And the main theorem that they proved is deciding whether Wx is at most θ or Wg at most θ is at most, the point is this quantity is at most tau times polylog in K. That is, if I give you a uniformly random bit string or uniformly random Gaussian vector, like the quantity Wx at most θ will look very similar if I give it either a bit string or if I give it a Gaussian vector. So that's their main theorem with which they prove their main PRG. And let me first sketch you in the next couple of slides how they prove this theorem. So the first thing that they do is they prove this thing called the smooth invariance theorem. So the point is they prove a weaker version of 1. And what I mean by weaker version of 1 is they first start with the smooth function O that takes Rk to R. And they say, okay, fine, let's just evaluate Wx. So recall W is a K by N matrix. So Wx is a K-dimensional vector. They first evaluate O on Wx or Wg. And they first try to understand how does O evaluated on Wx change when I evaluate it on a Gaussian vector. And they prove that this quantity is at most tau times log K times the L1 norm of the third derivatives of O. So O is a smooth function, so we can write the multivariate Taylor series expansion and look at the L1 norm. And the way they prove this is by the well-known Lindeberg method. So this was introduced in 1922 in order to prove several results in central limit theorem and also the Chernoff bounds. So they kind of mimic the same techniques that was done to prove the Lindeberg method. And so the way it goes is you write the Taylor series expansion for O, and then you observe that the moments of the uniform distribution and the Gaussian distribution have matching first and second moments. and we are left with the third moments. And that's precisely why you get the L1 norm of the third moments of O. Next, they observe that since O is smooth, and by smooth, I mean that all the derivatives are reasonably well behaved, like no derivative is very much larger than normal. So they observe that if O is smooth, then all the derivatives are well behaved. And then in particular, that means that the L1 norm of the third derivatives is also small. So this is just our intuition. So supposing O was a good approximation to this indicator function, then we kind of are in the right direction of proving equation 1. But this is the first observation that they had. For a smooth function, we can prove an invariance principle. Right, so this is what we have established so far, equation 3. And equation 2 is what we want. The next thing they observed is, as I said, we care about this indicator function Wx at most theta, not O applied to Wx. They used this very fantastic result that was established by Benkus in 1990, where what he says is you can actually approximate the Orton function using a very smooth modifier, that is B. In particular, what he showed is, think of B as a modifier that takes k bits, k real numbers to R. It's a very close approximation to max of I Zi at most theta. In a way, you should view this as Wx at most theta kind of says that the maximum value of Wx is at most theta I. So this is kind of exactly what's happening here. And B is kind of the Orton function that I'm going to be using eventually. Sorry, B is actually the modifier I'm going to be using eventually that approximates O. So the point is the O, which is the modifier, is I'm going to eventually use B for it, the Benkus modifier. But again, what needs to be shown is how does the L1 norm of the third order coefficients behave? What's very nice is Benkus modifier also satisfies that the Lth order, the L1 norm of the Lth order coefficients is actually polylogarithmic in K. So actually the point is if I just replace O with B, actually this quantity is just polylog in K times tau in the right-hand side. And we know morally that B is actually a very close approximation to the Orton function. So we're almost very close to being done. There's still one recipe that's remaining, and that's anti-concentration. So if you want to go from the Benkus modifier to the Orton function, we know that B closely approximates the Orton function, not exactly. So around the boundary of the polytope is where B and O disagree the most. So the interior of the polytope, B and O agree pretty well, and around the boundary, they have pretty strong disagreement. And how do the Harshad-Clemens-Mecca get around it? So the crucial insight that they have is maybe since we just care about the expectation over X or expectation over G, the probability mass of X sitting in the boundary of the polytope is small. And that is, and maybe if we can prove this, that could be okay. And precisely they show that this is fine. But in order to show that the probability mass is small in the first place, we require another additional step. And this is kind of like asking, is the Gaussian surface area of the polytope small? I mean, intuitively, the surface area is kind of measuring the size of the boundary of the polytope. And they kind of ask, does the surface area under the Gaussian measure, is it small for a polytope? Again, they use the seminal result of Nazarov in 2003, who showed that the Gaussian surface area of a k-facet polytope, that's k-facet on Rn, is actually square root of log k. It's independent of n, and it's actually square root of log k. And now if you put things together, actually, if you look at it, the point is equation 3, the right-hand side is tau times polylog k. And if you just need anti-concentration to go from 3 to 2, all the dependence is now just on log k, and that's exactly how they established 2. So they have this beautiful Benkus modifier, and then they have this fantastic result of Gaussian surface area. And if you put this together, we can actually show that we can actually show a smooth invariance principle and establish equation 2. So this is the main result of Harshad-Clemens-Mecca. And with several other techniques, they can actually get a pseudorandom generator for just regular polytopes. And let's look at what we need to worry about. So recall that again, half space was this, and a spectrahedron was kind of like summation xi ai is at most b, where this at most is in the lower ordering. And ai's are matrices now. So the first natural thing is just think of this as summation xi ai minus b being at most 0. That is the largest eigenvalue of summation xi ai minus b is at most 0. So in a way, a polytope and a half space just talk about real numbers, but a spectrahedra talks about the eigenvalues of matrices. So if I give you a matrix, a spectrahedra says is the largest eigenvalue at most 0 or at least 0. And it is very unclear whether we can use Lindeberg type of arguments for spectral modifiers. So what I mean by spectral modifiers is if I take a smooth function and apply it to the eigenvalues of matrices. For just applied to real numbers, which is what polytopes and half spaces, the works on polytopes and half spaces consider, those are fine. But if I look at the eigenvalues of matrices and then apply a modifier on top of that, we don't know if Lindeberg kind of argument could be generalized. And that's our first main result. What we show is an invariance principle for the Benkus modifier for arbitrary regular spectrahedra. We don't require positivity here, we just require regularity. The second result is, let's just say, I mean, there are two parts of the second result. The first is, let's just say, even if what was crucial in the previous thing is the result of Nazarov, which just says that the Gaussian surface area of polytopes is small. Let's say if the GSA of the spectrahedra is also small. Even if it was small, the boundary of a spectrahedra is actually very complicated. It's not very well understood. So even if supposing the GSA of spectrahedra is small, because they're such complicated looking objects, it's not clear how to go from modifier distance to CDF distance. So this is a very unclear part. I'll come to this in the last slide. But the main result that we show is we prove a Littlewood-Alford type of theorem for positive regular spectrahedra. So as I said, the point is the first result requires regularity. The second result requires regularity and positivity. We suspect that you should be able to remove regularity in both these results, and we could use the same proof techniques, but we have not been able to do so far. Fine, so the remaining talk, let me just sketch both these results. First thing I'll sketch is the invariance principle. So recall this is the quantity that we want to look at. So let me first define what's happening here. Summation xi ai minus b is what I spoke about in the previous slide. Circ lambda just means first look at the eigenvalues of this. So they're k eigenvalues because ai's and b's are k by k matrices. Look at the k eigenvalues of this, lambda 1 to lambda k. Apply the Benkus modifier on lambda 1 to lambda k. And I would like to understand what happens to the b circ lambda applied to this matrix when x is a uniform vector or x is a Gaussian vector. And the hope would be like similar to Harshad-Clemens Mecca, prove that this upper bound is tau times polylog in k. And we kind of mimic the same ideas that Harshad-Clemens Mecca do, is try to use the hybrid method. And in the pursuit of proving using the hybrid method, first what we do is we kind of hash 1 to n. So here summation I is from 1 to n, map hash n into t blocks. So we get qx, which is just this block, the first block that's from I from 1 to n to t. And one can re-establish the left-hand side of this inequality as the equation 4 now. I mean, it's just rewriting this inequality, this left-hand side of the first equation as here, equation 4. Next, what we do is we kind of try to do the Taylor series expansion of equation 4. So in the previous works, the Taylor series expansion just looks at the multivariate Taylor series expansion. But now we are kind of looking at matrix valued functions. So we need to look at something called the matrix valued derivatives, which are nothing but the Fréchet derivatives. So Fréchet derivatives are derivatives in Banach spaces. They kind of express the derivatives of matrix valued functions. And in particular, we're going to be looking at the Fréchet derivatives of spectral functions. And so we're going to write out the Fréchet series for both these terms in equation 4. So b subscript lambda is just b circ lambda applied to the matrix qx plus pxg. So it's the sum of the first order terms, the second order, this is the empty term, first order term, second order term, and the third order term. So most of the Fréchet series things kind of mimics the standard multivariate Taylor series expansion, but there are several properties of Taylor Fréchet series that are still unestablished, or that was just established in the last decade, which have been well known for several centuries even in Taylor series expansion theory. So we write out the Fréchet series for b lambda for the first term, and we write down the b lambda for the second term, and we have to subtract these two things. And what we observe is the same color terms are actually equal in expectation, where the expectation is over x and g. So red cancel, brown cancel, blue cancels. And what we are left with is just with the black terms. So if you want to understand equation 4, we need to show that the third order terms are at most tau times polylog in k. Right. So this is the goal. But as I said, like the understanding Fréchet series is not very well understood. In fact, there's several basic properties we are still trying to we still don't understand them about Fréchet series. But what's nice for us is we're kind of not working with arbitrary Fréchet derivatives. You're working with Fréchet derivatives of spectral functions. And there is this work in mathematical literature by Sendoff, who showed that there's actually a nice tensorial way to write the Fréchet series for a spectral function. So he actually gives us a slightly complicated looking expression that kind of at least helps us to understand the left-hand side of equation 5. So recall, we have kind of, in the previous slide, we wanted to show equation 5, and equation 5 would actually establish the first inequality on this page. So that's what we want to do. That's equation 6. And we would like to use a result of send-off. But if you write out this mathematical statement, you actually get this sum of 7 terms. And kind of, there's no need to understand these 7 terms, but what's important to observe is that the first 3 terms are actually the diagonal terms. And if you had to use a similar result, like the previous result of Arunachalam's Mecca and the subsequent papers, they just had to deal with diagonal matrices, which is nothing but polytopes. Because we're dealing with matrices, we actually need to deal with off-diagonal terms, which is 4, 5, 6, 7. So we need to understand the off-diagonal terms of these matrices. In particular, we need to bound 4, 5, 6, 7 by the upper bound in equation 6. We are not able to do this for arbitrary functions, but if we plug in f to be the Benkes modifier, what we show is that we can bound all these 7 terms by the right-hand side of equation 6. And this is the most mathematical cumbersome work of this paper. What we show is that with mathematical computations, we can actually bound all these 7 terms for the Benkes modifier by equation 6. So that concludes the invariance principle of our invariance principle theorem. Next, let's talk about anti-concentration. So far, what have we established? We have established equation 7. We have showed that B circ lambda, when we give summation xi ai minus b or summation gi ai minus b, is actually small. But as I said, what we want to do is we want to not just work with the Benkes modifier, we care about the orthon function, but with matrices right now. And kind of this approximation, I'll give you the intuition for this approximation now. This is kind of approximately what we want is this, and this is approximately already true. So if the eigenvalues of this matrix summation xi ai minus b was very close to 0, then this Benkes modifier, when applied to the eigenvalues of summation xi ai minus b, is very far away from deciding whether summation xi ai minus b is less than b or not. So if the eigenvalues of summation xi ai minus b are very close to 0, this approximation is bad. But if the eigenvalues are actually very far away from 0, if all the eigenvalues are far away from 0, then actually this quantity is a very good approximation of this function, indicator function xi ai minus b, xi ai being less than b. So again, as I said, we have been able to prove equation 7. We want to prove this thing. So we would like to go from B circ lambda to equation 8. And we know that this approximation is approximately true if the eigenvalues of lambda, all the lambda i's are not close to 0, are pretty far away from 0. And we're going to use the same idea that Arunachalam's Mecca did by proving that the mass of the xi such that the eigenvalues are small is actually very tiny. Or in some sense, if you pick a uniformly random x, the largest eigenvalue of summation xi ai minus b sits in a very tiny interval in 0, with the probability of that is very tiny. And we prove that by using the Littlewood-Offord theorem. And this is the second main technical result. We prove the Littlewood-Offord for positive spectrahedra. So let A1 to AN be positive matrices, such that we need this condition on summation I, the operator norm of AI square is at least 1. What we show is for every gamma, the largest eigenvalue of summation xi ai minus b sitting in this tiny interval is actually tiny in the first place. So summation xi ai minus b, look at the largest eigenvalue of it. The probability of it sitting in, say, minus 1 over 100 to 1 over 100 is actually just very tiny, just 1 over 100. So in some sense, because we know that the probability of lambdas being small is tiny, we can just, the point is equation 9 actually is very close to equation 10. So, right, so let me just, so before we prove this Littlewood-Offord theorem for spectrahedra, like the original Littlewood-Offord theorem was proven in 1943 for a single half space. Erdős improved that in 1945. He gave the optimum parameters. O'Donnell, Servideo, and Tan, a few years back, they proved the Littlewood-Offord theorem for polytopes. And what we do is extend all these 3 techniques to positive spectrahedra. And since the mass of the boundary of the eigenvalues being small, the probability mass of the largest eigenvalue being small is small in the first place, we show that 9 actually implies 10, except with the tiny probability, and that's good enough to prove our entire invariance principle. And this, along with some other techniques, kind of finally can be used to construct a final pseudorandom generator. And these other techniques are very similar to what Mecca Zuckerman did in their original paper, where they went from invariance principles to constructing pseudorandom generators. So let me conclude. So we had a positive spectrahedra, which is just summation xi ai being less than p. We say a PRG fools a positive spectrahedra, and the PRG that we constructed had seed length log n, polylog in k, m, and 1 over delta, where delta is the parameter with which we can fool the PRG, fool the positive spectrahedra. Here are some open questions. I think there are some natural open questions. The first one is, can we remove regularity? So after the work of Harsha, Clemens, Mecca, there was this work of Cerverio and Tan in 2017, where they kind of loosened the notion of regularity in Harsha, Clemens, Mecca before a subsequent work of O'Donnell, Cerverio, and Tan, where they completely remove regularity. Can we mimic the work of Cerverio and Tan in 2017 for the case of positive spectrahedra? That would be the first interesting result. And maybe eventually for just positive spectrahedra, can we completely get rid of regularity? The next question is, why even focus on positivity? Can we get rid of positivity altogether? So there is one natural barrier to this, and the barrier is most of these using this proof technique of Mecca Zuckerman of constructing invariance principle kind of requires a notion of anti-concentration. And anti-concentration kind of implies that the Gaussian surface area is small in the first place. If the Gaussian surface area was large, then it's not very clear how you would use this proof technique to prove an invariance principle and then construct a PRG. But that motivates the natural question, what's the Gaussian surface area of a spectrahedron? For polytopes, Nazarov showed that it's square root of log k, so it's polylogarithmic in the input parameters. In a recent work with Oded Regev, what we managed to show is for spectrahedra, arbitrary spectrahedra, which need not be positive, the Gaussian surface area is actually n to the 1 over 8. Contrast this with polytopes, which was actually square root of log n. So if you want to use this technique of invariance principles to construct PRGs, you need to somehow recall that the Gaussian surface area is actually an important tool, and it's large for spectrahedra. So it's not completely clear whether this positivity, if you have to remove this positivity, you might require new proof techniques altogether. Whereas if you want to keep positivity and remove regularity, potentially you could use the same proof technique and just maybe with some new ideas, you could remove regularity. The final thing is, can you improve the 1 over delta dependence? So in this original work of Diaco-Nicolas and Mecca Zuckerman, and also a follow-up work of O'Donnell et al., they kind of improve this 1 over delta dependence by using some ideas from read-once branching programs, for which we can improve the 1 over delta dependence to log 1 over delta. Potentially, you could do something similar for us as well. And the final thing is, we proved an invariance principle for just spectral functions acting on the Bencus modifier. This was also done in the prior work of O'Donnell, Cerverio, and Tan for fooling polytopes. So the point is, our general invariance principle is just for the spectral function, where the function is the Bencus modifier. Can you prove a general invariance principle for arbitrary spectral functions? Potentially, this could have other applications in quantum computing as well. With that, I thank you for your attention.